Hello my dear friends, I am Shubham from Learn Hub, the free learning platform where you can study physics, chemistry, maths, biology absolutely for free at learnerhub.com. So then, let's start. So students, in this video we are going to study your ICSE class 9th chapter number 5, the periodic table. Okay, and in the previous video we have covered some concepts of your periodic table. Okay, if you have missed that video, please do give a watch, because we have discussed a very interesting story of the development of the periodic table. Right now in this video we are going to continue with the remaining concepts of this chapter. Also we are going to see some questions at the end of the video so that you would get an understanding how much you have understood, okay, whatever the things we have learned in the video. Fine, so without wasting much time, let's start and let's rock. Okay, so students, so far we have seen the initial efforts by de Bruiner to arrange the elements, then Newlands, and then finally Mendeleev, right, in the previous video. Now, what happens after Mendeleev then? Okay, who comes and takes up the baton? So here you can see this very much like dashing person's image, and he is looking, I think, towards you only, but I'm just joking. The Henry Moseley, okay, he was the one who actually told the entire world that the atomic number is simply the number of positive charges present in the nucleus. Okay, number of positive charge. So can you just correlate with the definition of the atomic number which we have studied in the previous chapter, right? What was atomic number? Number of protons in the nucleus, right? And protons have positive charge. Okay, so in short, Moseley gave us the exact meaning, or exact what is atomic number is meant by, okay, through his experiments. So simply here the number of positive charge in the nucleus means the number of protons in the atom, okay, or number of protons present in the nucleus. So his means like explanation of what atomic number was not enough, okay, for us to move ahead and make a different arrangement for the elements, because after his researches and experiments, okay, what he told us was the thing which revolutionized the way of arranging the elements, and this concept or this thing was used at that time, and the periodic table of elements which we know right now was developed. And what was that thing? Okay, he told us that not the atomic mass but the atomic number is the fundamental property, or more fundamental property of an element. Okay, atomic mass is, yes, quite a fundamental property of an element, but more than the atomic mass, atomic number of that element, okay, or atomic number of the atom of that element, okay, is more fundamental than the atomic mass. Okay, and this atomic numbers, like popularity, or atomic numbers more fundamental nature, okay, was used by Moseley, and he gave us the so-called modern periodic law. Okay, so Mendeleev's periodic law was the first one, right? But modern periodic law was the law given by Moseley, and this was the second law which helped us to reach the arrangement of the periodic table which we are using right now. And what that law is, a slight modification of the Mendeleev's periodic law, a very slight modification. Okay, in place of atomic masses, he just replaced the term atomic masses, Moseley, and put their atomic numbers. So you can see the physical and chemical properties of the elements are the periodic functions of their atomic numbers. Okay, now I have already explained you the Mendeleev's periodic law. Okay, what that meant was simply, if I would take elements, okay, suppose I would start with lithium, okay, now its atomic number is like 3, and I would progressively move on to the elements having higher atomic numbers. I would encounter sodium, okay, now this element's atomic number is 11, but when I would encounter sodium, I would see that, oh, the properties of sodium are similar to that of the lithium, and then again I would move on, okay, to the elements having higher atomic numbers and so on, I would again encounter an element called potassium whose properties are like matching with sodium as well as with lithium, and this goes on and this continues, and again I would move ahead. Okay, means again I would, okay, if I would go from this potassium to the elements having higher atomic numbers, I would reach rubidium, and this element would again have the properties similar to that of the potassium, sodium and lithium. Okay, so what I have observed is, okay, or what Moseley told us from his law is that if you would, okay, arrange the elements in the increasing order of their atomic numbers, you would get the elements having similar properties. Okay, see, I got an element having similar property, again I got an element having similar property, again I got an element having similar properties. Okay, after particular interval of the atomic numbers. That's it. Okay, so this is a particular interval. After a certain interval I got potassium, after a certain interval from potassium I got rubidium. So this is what actually Moseley wanted to tell us, but you know, the scientific language is like too heavy to understand, and it is always like a bouncer in cricket. Okay, so don't duck that bouncer, play a shot on that bouncer. Okay, try to understand and what actually the scientists mean from their laws, because they actually tell us very simple things. Clear? And most of the students don't try to understand the periodic laws, they just try to memorize the periodic laws, and that doesn't help. Okay, you won't enjoy the learning because you would simply memorize and you won't understand the logic behind the things happening in the science. Very interesting. So this was very simple thing told by the Moseley, exactly same as that of the Mendeleev, but just here he told that you would get the elements having similar properties after a particular interval of atomic numbers. Fine, and this is what is called as periodicity. Very simple. Okay, now the reason behind the periodicity we can understand with the help of this atomic numbers. Why? Because in the previous chapter we have studied, based on the atomic number we were able to write the electronic configuration, because atomic number told us or give us the number of electrons present in the neutral atom, and once we know the number of electrons present in the neutral atom, we arrange those electrons or we distribute those electrons in the different orbits. Correct? So here also, since we are getting the elements after a particular interval of the atomic numbers, so when we observe the electronic configurations of such elements, okay, for example, I am getting lithium, sodium, potassium and rubidium, these elements which are having similar properties and after the particular interval of atomic numbers. But when I encounter their electronic configurations, for example, suppose lithium is 2,1, sodium is 2,8,1, potassium is 2,8,8,1 and so on. If I would move on to rubidium and then cesium and so on, okay, what I would observe is, you can see here the outermost orbit, okay, is having one electron. In case of lithium, in case of sodium also it is having one electron, in case of potassium it's also having one electron, in case of rubidium and cesium also, if you would write its electronic configuration, no need though right now, okay, but if you would write the electronic configuration for rubidium and cesium, okay, we would also get one electron in its outermost orbit. Okay, so this means that, okay, since they are having the same or similar, okay, so called similar outer electronic configuration, okay, this is called as electronic configuration, right? We all know 2,1, 2,8,1, 2,8,8,1. These all are electronic configurations, but we are now talking since about the outermost orbits or outermost shells, okay, and since these outermost shells are having same number of electrons, okay, so that's why we are saying that they are having similar outer electronic configurations, okay, or we can say similar outermost shell electronic configurations, and since they are having similar outer electronic configurations, they are showing similar properties. Okay, so the reason for the periodicity is simply that the elements are, since the elements are having similar outer electronic configurations, that's the reason they are showing similar properties. That's it. Clear? Very simple concept. But now we are going to stop we are going to take a break on this periodicity concept, because the more we are going to learn in your next class. Fine, the periodicity and also the periodic properties and all those things. Fine, now we are going to focus that how this law is being used to arrange the elements and to make the so-called modern periodic table which we use right now. Okay, so now by making the use of modern periodic law, whatever was said in that modern periodic law, that the elements, the properties of the elements were observed to be similar, okay, after a particular interval of the atomic number when we are arranging the elements in the increasing order of their atomic numbers, right? Simple. So what we did for making the modern periodic tables, we simply arranged the elements, okay, in the increasing order of their atomic numbers. Okay, now here the arrangement was similar to that of the Mendeleev's periodic table. Okay, the arrangement was in the increasing order of the atomic numbers, but in the form of a table, right? That is horizontal rows and vertical columns. You can see here, these are the horizontal rows, right? See, fine. This one, okay. So these horizontal rows are called as periods. Okay, you have to remember this thing. Here the horizontal rows in the modern periodic table are called as periods, and the vertical columns, okay, you can see here, these are the vertical columns. Okay, these are called as groups. Clear? So I hope it would be clear to you now what are periods, what are groups, and exactly the same manner in which Mendeleev's periodic table was made, here also modern periodic table is also made in the same manner, but here we are just changing one thing. In place of atomic mass, we are putting atomic number. That is, we are arranging the elements in the increasing order of their atomic numbers in the horizontal rows called periods and vertical columns called as groups. But we are taking care of one very important thing which we also have to, which was also taken care of when the Mendeleev's periodic table was being made. That is, the elements having similar physical and chemical properties would be placed in the same vertical column, or we can call it as group. Okay, so whatever groups you are able to see here, okay, suppose like lithium, sodium, potassium, rubidium, cesium, francium, okay, or beryllium, magnesium, calcium, strontium, barium. So these are the elements having similar physical and chemical properties, and they are placed in the same group. Okay, just don't pay much attention to this middle block of elements. Okay, these elements are having characteristics slightly different, but you can just pay attention to these two groups or this 6 groups. Okay, here the elements in the same group are having similar properties. Very clear? Okay, so this was being also followed when making modern periodic table. Now more about the modern periodic table is like, there are so many versions of modern periodic table. Okay, but the most widely used and very much convenient for us to use is the long form of the periodic table. Clear? Now before getting into more details of the long form of the periodic table and how the elements are arranged and how many periods, how many groups and all those things and all those stuff, we would just have a look over the demerits of the Mendeleev's periodic table, and let's try to figure out whether this new periodic table is like eradicating or is able to eradicate all the demerits of Mendeleev's periodic table or not. Okay, so now the very first demerit was anomalous pairs, the cobalt and nickel anomalous pair, as well as the tellurium and iodine anomalous pair. Now have a look over the modern periodic table. Okay, now as per the Mendeleev's periodic table, okay, initially tellurium was given the position, and after tellurium iodine was given the position, though their atomic masses, okay, here the tellurium's atomic mass was higher than that of the iodine. Okay, so we were arranging the elements in the increasing order of their atomic masses, right? So first iodine should have come, then tellurium should have come, correct, ideally, if we are following the increasing order of the atomic mass. But Mendeleev slightly did the opposite thing, though he knew that the elements, okay, if I would place them in the increasing order of their atomic masses, iodine would come first, tellurium would come later on, but still he placed tellurium first and iodine later on, just because iodine should be placed with his own brothers and cousins, which are fluorine, chlorine and bromine. Okay, I am joking. Iodine should be placed with those elements having similar properties like fluorine, chlorine and bromine. Okay, so in order to stick to his second criteria, in order to stick very much firmly to his second criteria, that is placing the elements having similar properties in the same group, Mendeleev just ignored his first criteria, that is arranging the elements in the increasing order of their atomic masses. But here when we would observe the modern periodic table, okay, it should be exactly like this. Tellurium should be first and then iodine should be placed. Okay, because iodine should be placed with the elements having similar properties, that is fluorine, chlorine and bromine. And you can see here tellurium is placed before iodine, but the atomic number sequence or the atomic number order is not disturbed. Okay, because tellurium's atomic number is 52, iodine's atomic number is 53. Okay, so both the criteria are getting satisfied. The increasing order of the atomic number, that is tellurium 52, iodine 53, got satisfied. Also, the elements having similar properties should be placed in the same group. So iodine is exactly placed in the same group as that of the bromine, chlorine and fluorine. Okay, so here that anomaly was removed. So by using the arrangement, okay, or by using the increasing order of the atomic number, the anomalous pair anomaly got removed. Okay, also you can have a look over the another two elements, another anomalous pair, that is cobalt and nickel, right here. See, so the same logic goes to the cobalt and nickel as well. They were placed by Mendeleev like this only, cobalt and then nickel. Okay, but their atomic masses were not following the increasing order. But when you would see, okay, in the modern periodic table, they are still placed as cobalt and nickel, but their atomic numbers are following the increasing order. See, 27 cobalt, 28 nickel. Clear? Got the idea? Now, moving ahead, the next demerit of Mendeleev's periodic table was also eradicated, that is position of hydrogen. So we know that hydrogen is resembling with both this so-called alkali metals, which are like this group 1, lithium, sodium, potassium, rubidium, cesium. Okay, it is resembling with this also, as well as, okay, don't worry, I'm calling them as group 1 and all those things. You just remember that these are the alkali metals. For now, you would get a better understanding in few minutes. Okay, so since hydrogen was having like similar properties to this first group, lithium, sodium, potassium, rubidium, cesium, as well as similar properties to this group, fluorine, chlorine, bromine, iodine. So Mendeleev couldn't give hydrogen a specific position, okay, neither towards the alkali metals nor towards the halogens. But in modern periodic table, hydrogen, since it is having properties resembling to both this type of elements, so it is being given a special position, that is in the center of the periodic table. So that also problem got solved. Clear? Next is position of isotopes. Now isotopes are simply the atoms of same elements having same atomic numbers, right? So though a particular element is having 2 or 3 isotopes, okay, for example carbon, okay, so carbon 12, 12, 12, okay, fine. So though they are having same atomic numbers, since they are having same atomic numbers, though they are having different atomic masses, like 12, 13, 14 is their mass numbers, so this means that their masses are also like different. Okay, so though they are having different atomic masses, but we don't care about the different atomic masses, we care about the same atomic numbers. Okay, now since the atoms of these elements are having same atomic numbers, so we would give them same position, right? And since they are atoms of same element, we would definitely give them the same position. Means both the criterias are getting satisfied. Since they are atoms of same element, we would give them same position. That's the correct thing, okay, which we would follow. But since they are also having same atomic number, so no question arises of giving them different position. They should be given same position. So that's the point. So isotopes, the position, which position should be given to isotope or how isotopes should be placed, that also got clear. Okay, that problem was also got solved. Okay, since there was no need to give different position to the isotopes, we can just accumulate the isotopes in the same position. Clear? Now moving ahead, the third one is when you would observe the elements which are placed in the modern periodic table. Okay, so here the atomic numbers are increasing in the regular manner. Okay, for example, from lithium atomic number is 3, then beryllium it's 4, okay, then boron it's 5, carbon it's 6, nitrogen 7, like this way. Okay, and if you would see 11, 12, 13, 14, 15, 16, 17, 18, atomic numbers are like increasing in very regular manner, 19, 20, 21, 22, 23, 24, 25. Now you would say, sir, these are like lighter elements? Okay, what about the heavier elements in which the anomaly or in which the demerit of Mendeleev's periodic table was there? So if you would see also the heavier elements, okay, you would definitely find that the atomic numbers are increasing in very much regular manner. Okay, the difference of only one atomic number unit. Okay, like you are here 104, 105, 105, 106, 107, 108, 109, 110. So very regular. Okay, not even a single element is present. Okay, or not even a single instance you would find where the atomic number difference is more than 1. So very regular. So this made it very clear that in between the two elements, okay, though they may be heavier elements, but since the difference between the atomic number is only 1 unit, so there is like a very rare possibility of an element having like which can be discovered later and which could be placed between these two elements. Clear? Okay, so this also anomaly got like solved, and in this way we have seen that all the 4 anomalies, like regular increase in the atomic number, irregular increase in the atomic mass was the anomaly in the demerits, or was the demerit of the Mendeleev's periodic table. Here the position of isotopes was not confirmed in the Mendeleev's periodic table. Also position of hydrogen was not like final, and the anomalous pair. These 4 demerits we have just now seen, and these all these demerits are being solved in our modern periodic table. So yes, we have busted the demerits of Mendeleev's periodic table by bringing in the modern periodic table. Okay, so students, let's move ahead, okay, and let's see how our long form of the periodic table, okay, or how the elements are arranged in the long form of the periodic table, right? Yes, but before that, one very minor mistake, okay, that is, yeah, I have just here mentioned 12C6 and 13C6, okay, like 12C12 and 13C12 and 14C12, it's like slightly incorrect. Here it's 12C6, 13C6, 14C6. Okay, these isotopes are having atomic number, okay, as 6 because these are isotopes of carbon. Okay, their atomic number is same, and yes, it's 6, not 12. Sorry for the minor mistake. Now yes, moving ahead to the long form of the periodic table, the elements are arranged in the horizontal rows, which are called as periods, right? You can see here the horizontal rows, and the vertical columns, okay, which are called as groups. We have already seen this, but how many groups are there in our long form of the periodic table? It's very simple. Okay, there are total 18 groups. Fine. And earlier the notation of the groups was like quite confusing, but no need to go into those details, or no need to go into that much difficult notations, because finally, okay, in your exams also the new notations given by the IUPAC, okay, are being accepted. So the new notations are quite easy for the for the groups. It's simply 1 to 18. So you can see here, this is the first group, right? This one, the first group, okay, group number is 1. Then the next group's number is group 2. This is the group 2, okay, and then so on. So this is group 3, group 4, group 5, okay, and this continues, group 6, 7, 8, 9, 10, 11, 12, and then again to group 13, okay, group 14, 15, 16, 17, 18. Fine. Now you would be amazed and surprised to know that every groups, okay, or the elements present in the every group, okay, there is a very interesting chemistry behind these elements. But don't worry, we are not going to bombard into the chemistry of these so many elements, like 118 elements. At this level, in this chapter, we are only going to superficially see what is actually, means how the elements are being arranged and all those things. Okay, in the next next standard also we are going to see the periodicity part, and then you would study, okay, the slightly the properties of group 1, group 2, okay, group 17 and group 18 elements in the next standard. And in this chapter also we are going to slightly have a glimpse of the properties of these 4 groups. Which groups? Group 1, group 2, group 17 and group 18. But let's keep it for later on. Okay, we are going to separately see their properties. For now, it's fine. These are the 18 groups. Now, one very much interesting thing you can see here in this third group, okay, here at this point and here at this point, okay, we are going to see there is like a slight variation in the arrangement of the elements when we would study the periods. Okay, just to remember it for right now. Okay, now There are 18 groups. Out of these 18 groups, this group 1, group 2, okay, this entire groups which are in blue, you can see here, and from group 13 to group 18, this entire group 13, 14, 15, 16, 17, 18. Fine. All these groups, okay, all these 6 groups and these 2 groups collectively, okay, are called as main group elements or representative elements or normal elements. Okay, so this is just the name given to this group of elements. Fine. So you have to remember group 1, 2, and then 13, 14, 15, 16, 17 and 18. Clear? Clear? Very much clear to you. Now the rest groups, you would say, sir, is there any name for them? Yes, definitely, but there is a slight trick in this or slight twist in the story. What remaining groups are, apart from 1, 2 and 13 to 18, there are now groups from 3 to 12. So you would say, sir, these 3 to 12 groups would also have some name. Yes, they have some name. Okay, they are called as transition, means the elements present in these groups are called as transition elements. Okay, the elements present in the group 1, 2 and 13 to 18 are called as main group elements or representative elements. So elements placed in the groups from 3 to 11, okay, not 12, okay, from 3 to 11 are called as transition elements. Fine. Okay, not group 12. And you would say, sir, why not group 12 is included? Okay, or why not the elements in the group 12 are called as transition elements? The reason behind that story you would understand if you would have known the quantum mechanical model of the atom, but we all know we haven't studied that. Our syllabus has limited us till the Niels Bohr model of the atom. Okay, so you would study definitely that model in your grade, means class grade 11 or grade 12, something like that. But for here right now, no need to worry about why group 12 elements are not included in transition elements. You just remember from group 3 to group 11, the elements in these groups are called as transition elements. Fine. Moving ahead, let's see about the periods then. So the horizontal rows are called as periods, and you can see here, okay, the hydrogen is, since it's placed, okay, in the center, but still we believe that it is the element of period number 1. Okay, still we believe it. Okay, so in the first period we have hydrogen and then this, a very cornered element, helium. Okay, and then again here this is the second period, the second horizontal row, then this is the third period, third horizontal row, fourth period, fifth period, sixth period and seventh period. Okay, so in total we have 7 periods. Fine. Now the very interesting thing about the period is whatever the period number is, okay, in that particular period, whatever the elements are present, okay, all those elements would have the number of shells same as that of the period number. Let me explain you. Okay, don't worry. Suppose I am talking about period number 2. So all the elements present in the period number 2, okay, their atoms would have 2 shells. Fine. All the elements present in the period number 3, their atoms would have 3 shells. Similarly, all the elements present in the period number 4, their atoms would have 4 shells. Fine. What do I mean by 2, 3 or 4 shells? I mean that their atoms would have electrons, okay, in their 2 shells. Here the electrons are present in the 3 shells. Here the electrons are filled in 4 shells. Okay, so I'm basically telling the number of shells which are filled with electrons. Okay, so if I'm talking about the period number 2, all the elements, okay, here, so atoms of all the elements in the period number 2, okay, would have electrons filled in their first 2 shells. Here all the elements present in the period number 3, okay, their atoms would have electrons, okay, filled in their first 3 shells. Okay, similarly all the elements, okay, or the atoms of all the elements present in the period number 4, okay, their atoms would have electrons filled in their first 4 shells. Clear? Got this very simple analogy? Okay, now moving ahead, let's see the type of the periods and the number of elements present in the each period. So the first period is the shortest period because it is having only 2 elements. Okay, so I'm just writing here period number 1. Okay, the type is shortest. Fine, you can see only 2 elements. Okay, because I have told you just we have to we need to just consider that hydrogen is the element belonging to the first period, though it is placed in the center, but we believe that it is the element of first period. So first period is having 2 elements, hydrogen, helium. Clear? So number of elements is 2 for first period. Fine. So first period number of elements 2. Since it is having 2 elements, okay, the least number of elements, so that's why its name is shortest period. Next, the period number 2 and period number 3. These 2 periods are having 8 elements each. Fine. So you can count from lithium to beryllium, then boron, carbon, nitrogen, oxygen, fluorine, neon. There are 8 elements. 6 plus 2, 8. Similarly here also 2 plus 6, 8. So second and third period are having 8 elements each. Fine. Second and third period. Okay. Okay. Now these 2 periods are called as short periods. Fine. This is the shortest one because it is having 2. Since they are having 8, so like more number of elements than the first. So that's why from shortest to short. Again, period number 4 and period number 5, okay, has 18 elements. Now you tell me what would be their name then. Okay, it's like quite obvious since they are having 8 elements. Okay, period number 2 and 3, and since their name is short, so since they are having 18 elements, period number 4 and 5, so more number of elements then they would be something more than the short, that is long, right? So these are called as long periods. And lastly, 6th and the 7th period, fine, okay, have 32 elements each, and they are called as longest periods. Okay, so we can see here, okay, first period number of elements 2, second and third number of elements 8. You can count on your own as well, okay, in order to remember. See, this fourth period is having 18 elements. You can count it from potassium to krypton. Okay, and then again the fifth period is having 18 elements. Okay, from rubidium to xenon you can count. But then now you would be surprised to know that, sir, we can see the length of the 6th and the 7th period same as that of the 4th and 5th period. Okay, and if I count the number of elements in the 6th period, okay, it's 18. Number of elements in the 7th period, it's 18. So why you have written 32 elements here, sir? Okay, why so? Because you would have missed this remaining 14 elements each in those periods. Okay, now these 2 rows of 14 elements, okay, belong to, see this position, the period number 6 and group number 3. Okay, so when we go from when we are in the period number 6 and group number 3 at this position, okay, there are, along with this element, okay, which is called as lanthanum, there are another 14 elements, okay, present here. So if then now you count, so these are 2, okay, elements, 3, then this 14, so 14 plus 3 is 17, correct, and then 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Now you got the point, how there are 32 elements. Now let's see about these elements as well. Okay, why are these placed below and all those things, and here what are actually these elements are called. Okay, but before that, first let's have a basic understanding about the atomic numbers, okay, in the particular period, or the atomic numbers of the elements present in the particular period. It's very easy, it's very simple. See, the first period starts with hydrogen. Okay, you have to just observe the periodic table. All the things you would understand whatever I'm telling to you. Fine. So just first see the periodic table nicely. The first period is starting from hydrogen. Okay, the hydrogen's atomic number is 1. Okay, you can see the atomic number at the top of the element symbol. Okay, in your book also the atomic number would be specified correctly. So hydrogen's atomic number is 1. So I'm writing here first period, it's starting from hydrogen. Fine. Okay, now its atomic number, I'm writing atomic number here down, okay, 1, because we represent the elements symbol as AXZ, right? So no need to write the mass number, we are just talking about atomic numbers. So I would just write the symbol and the atomic number, that's it. So hydrogen 1 to helium 2, right? Because there are only 2 elements in this period, from hydrogen 1 to helium 2, correct? The next period starts from lithium, second period. Okay, so lithium's atomic number is 3. Okay, you can see here in the periodic table. I'm not doing anything super magic. Okay, I'm just observing the periodic table and writing the elements, okay, which is the first element of that period and the last element of that period. Okay, but then I would also tell you the trick to remember the atomic numbers of the first and the last element of the period. Okay, so please pay attention here. Okay, the trick you would understand if you would pay attention. So here lithium atomic number 3 to neon 10. Okay, you can observe, okay, there is at that end there is neon, lithium 3 to neon 10. Fine. Moving ahead to sodium 11, okay, to argon 18. Clear? So this is the third period. The fourth period is starting from potassium 19, okay, see here, potassium 19. Now here sodium 11 to argon 18, potassium 19, okay, to krypton 36. Fine, and so on. So rubidium, the next one is rubidium 37, okay, to xenon 54. Okay, so I'm just writing here rubidium 37, xenon 54, and cesium. Okay, this is the fifth period. Sixth is from cesium 55 to radon 86. Okay, and the last one is seventh period. It is starting from francium 87 to organosen 118. Clear? Now, how I can remember, or how I have remembered the elements, okay, the first element of the particular period and the last element of the particular period. Very easy. You just first remember the first elements, okay, in a line. Okay, so you would definitely memorize lithium, sodium, potassium, rubidium, cesium, francium. Okay, so the analogy or the trick here I'm sharing with you is like this: LINAC, okay, LINAC, okay, and then you can write here RBCs. Now, okay, if you have studied bio enough, so you would be knowing RBCs. If you don't know, no worries. Okay, these are the cells which are very important in our body. Okay, red blood corpuscles is their full form. No need to dive deeper into that biology thing. Okay, just needed the abbreviation. Okay, because here RB is rubidium, CS is cesium, and then you can just write Fra. Okay, so these are the elements, okay, which are the starting elements of the periods. And before lithium, the first period starting element is hydrogen. Now you would have remembered it. So then hydrogen, then LINAC, RBCs, Fra. So you can see here hydrogen, LINAC, RBCs, Fra. Clear? Now the last elements of those periods are hydrogen to helium. You would have remembered, but still I would give you a simple, okay, means still you remember in the rhythm. Okay, what I do is I have remembered from my childhood in the rhythm. So helium, neon, argon, krypton, xenon, radon. Okay, in this rhythm. So you can put any interesting rhythm to you. So like helium, neon, argon, krypton, xenon, radon. So any music tune you pick up and put it here. Clear? So here see helium, neon, argon, krypton, xenon, radon, and the last element, okay, of the last period is this OG, okay, organosen. So you can remember this because it's the latest element, okay, latest. The most recent element which is discovered is this organosen. Fine. So remembered all the starting and the ending elements. Clear? Now the atomic numbers is the thing which would bother you, because maybe you won't have the periodic table in front of you. Then how to remember the atomic numbers? So first you would start with hydrogen. Fine. Let me tell you the simplest trick which would help you to remember the atomic numbers as well. Okay, see. Okay, here the first period is having 2 elements. So hydrogen and helium, that's it. So what I would do is, from first period's atomic number, I would add 2. So I would get the atomic number of the next period's first element. That is 1 plus 2 is 3. Perfect. The second period is having 8 elements. Now I know in my brain. So I would just add 8 in this 3. I would get the atomic number of the first element of the next period. First element of the next period. That is 3 plus 8 is 11. Same way, third period is having 8 elements. I know. So 11 plus 8 is 19. See? Okay. And then I know fourth period is having 18 elements. So 19 plus 18 is 37. Okay, you can calculate. If your math is so strong, you can just quickly calculate, okay? Because 19 2s are 38, minus 1, 37. And again, I know fifth period is also having 18 elements. So that's the reason I have already discussed with you the number of elements in a particular period. So fifth period is also having 18 elements. So just add 37 plus 18. Okay, you would get, absolutely you would get 55. Okay, so here it's 55. And then I know sixth period is having 32 elements, right? So add 32 with 55 and then you would get like 85, 87. Okay, so the atomic number of the next means the atomic number of the element which is the first element of the next period. Okay, that is 87. Clear? The same trick you apply for this side as well. From helium you add 8 because next period is having 8 elements. Okay, see here, after helium next period is having 8 elements, so add 8. Okay, just you need to remember that next period is having how many elements. So when we were starting here, okay, here you need to remember that particular period is having how much element. This is having 2 elements, so plus 2. This is having 8 elements, so plus 8. This is having 8 elements, so plus 8. Okay, but when we are writing the atomic numbers of the elements which are the last elements of that particular period, so what you need to do is you need to see the number of elements present in the next period. Fine. Or simply you can just add the number of elements, okay, from this first element to the last element. Means like 3 plus 7 you get 10. And now why 7? Because you are including this third element as well. Okay, so anyway you can do, that's the simple math behind the atomic number trick, okay, which you can use. So I definitely use this trick. Okay, what I do is I know first period. Now for this side, I know first period is having 2 elements, but the second period is having 8 elements. So I add plus 8. Then again, the third period is having 8 elements. So I do plus 8. So 18. Now I know that, now I'm talking about the fourth period's elements atomic number, the last elements atomic number. So fourth period is having 18 elements. So what I would do is plus 18. See, fourth period is having 18 elements. So plus 18, 36. Fifth period is again having 18. So 36 plus 18 is 54. I got 54. And then sixth period is having 32 elements, so I would add 32 here. 86. Seventh period, the next period is also having 32, so I would add 32 here. So 86 plus 32 is 118. Clear? Very clear, very simple trick. Okay, now friends, let's see the very much secret thing which we have kept so far is the elements, okay, which are placed in the sixth period, right, third group, right, and this seventh period and the same third group. Okay, about these two elements, let me tell you what are these elements. Okay, so in this position, sixth period, third group, okay, 15 elements are placed. Fine, and those 15 elements are called as lanthanoids. Okay, lanthanoids. Now in your textbook maybe they have been written, they have been mentioned them as lanthanides. Okay, but here, okay, IUPAC has suggested, okay, IUPAC is a body, right, which modifies the, which takes care of the chemistry concepts, okay, concepts of the chemistry, and which takes care of the modification, because gradually, slowly and gradually, the things are going, things like slightly change, new in experiments lead us to newer discoveries, and that's why IUPAC is a body of chemistry, okay, which tells us the modifications or changes or like updates like you have in your mobile apps about the updates of the chemistry. So that body has told that not to use lanthanide word for these 15 elements which are placed here. Okay, instead use lanthanoids. Fine. Okay, now in the same manner, the elements which are present in the seventh period and third group, okay, there are also 15 elements. They are called as actinoids. Okay, not actinides. Now the reason is the same thing. IUPAC has asked us not to use actinide, okay, nide ending, okay, nide as the suffix, use noids as the suffix. Fine. Now what are these 15 elements, or now what we are going to do is we are not going to learn all these 15 elements. We are just going to remember the first and the last element of this group of 15 elements. Okay, now lanthanoids is the group of 15 elements, okay, present in the 6th period 3rd group. So these lanthanoids start from, now word lanthanoid, okay, so elements are starting from lanthanum. Okay, so first element is lanthanum itself. Fine. And then, okay, the last element is lutetium. Okay, so how you would remember this? Just remember in a rhythm, la lu, right? So la lu. Fine. And the atomic number is 57, okay, of lanthanum, and lutetium's atomic number is 71. Now if you want to remember, means you should remember the atomic numbers, and how you can remember is you just remember the first, means the lanthanum's atomic number, and then simply add 14 in it. Okay, now adding 14 in it is a very logical thing, because since these are the group of 15 elements, okay, we know the first element's atomic number. Now rest, how many elements are remaining? 14 elements are remaining. Therefore add 14 in it. That's it. Then we would get the atomic number of the last element. 57 plus 14, 67, 4, 71. Okay, so lutetium. Now the same way, the group of 15 elements present in the 7th period 3rd group, right, are called as actinoids. I have told you they also start from the word actinoid. Okay, you just remember they start from actinium. Okay, so yes, actinoids start from actinium. Remembering? Okay, getting the point? Now first element is actinium, last element is lawrencium. Okay, Lr. Okay, this is last element, this is the first element. Actinium's atomic number is 89, lawrencium's is 103. How you can remember? Remember the actinium's atomic number, simply add 14 in it, you would get 103 lawrencium's atomic number. The logic is same as that of this. Okay, because since it is the first element, next 14 elements are remaining, therefore add 14 in it, we would get lawrencium's atomic number, 103. Very simple about lanthanoids and actinoids. Now there would be a question in your mind, sir, why these elements are placed at the bottom of the periodic table? Why at the bottom? Why can't we place it here itself? Okay, now the reason here is because, see, we have studied that elements, okay, in this long form of the periodic table are placed in such a way, or in the modern periodic tables are placed in such a way that the elements having similar properties are occupying the same groups. Okay, so now this group, for example, suppose I'm taking group 14. Okay, so now this group 14, fine, okay, excluding the last element of the group 14 because they are like recently discovered, so I'm not talking about them. This group 14 has carbon, silicon, germanium, tin and lead as their elements. All these elements are like having similar properties to each other. But if I would place, okay, this group of 15 elements, okay, two groups of 15 elements, that is lanthanoids and actinoids. Okay, from now onwards I will call them as lanthanoids and actinoids. So if I would place lanthanoids and actinoids here, okay, what would happen is they would shift this entire, like, I would highlight it, okay, they would shift this, fine, this row and this row of the elements. Now forget about the last row, it's okay, if means now they would shift the last row as well, okay, but focus on this row, okay, the second last row. Now if this would shift, would our lead be in the same position then, right? Would our lead remain in the same position then? No, because this would shift ahead. So our lead would be shifted ahead. So our now lead would not be placed with the group of elements, okay, or with those elements which are having similar properties. And our criteria for placing the elements in the periodic table is to place the elements having similar properties in the same group. Now this criteria would get disturbed, right? Because lead would get shifted ahead. In the same way, bismuth would get shifted ahead. In the same way, our thallium would get shifted ahead. Okay. In the same way, polonium would get shifted ahead. Now these elements, now they won't have the position, okay, or they won't be placed in the group, okay, having the elements properties similar to those elements. Trying to get it? Just simply taking the example of lead, you could understand that if I would place these two group of elements here, it would shift these two rows of elements, and our lead won't be now in this position. So our now lead won't be with those elements which are having similar properties like that of lead. Okay, and our criteria is to place the elements having similar properties in the same group. But now lead would not be in the same group. Understood? So for this reason, we place lanthanoids and actinoids at the bottom of the periodic table to maintain the second criteria of arranging the elements. Okay, that is placing the elements with similar properties in the same group. Now, just for your info, okay, we are not supposed to study the classification as per the blocks, so-called blocks, but since we have studied so much about the periods and groups, it would be easy for you to right now, okay, just have a glimpse of the classification of elements as per the blocks. So this group 1 and group 2 elements, okay, are called as S block elements. Okay, not considering hydrogen. Okay, we are not considering hydrogen in S block, just simply group 1 and group 2 elements. Fine, S block elements. Then this group 13 to group 18, all elements here are called as P block elements. Okay, and then this D block elements are from group 13 to group 12. Okay, now here group 12 is included. Fine, and here the 14 elements, okay, after lanthanum and 14 elements after actinium, okay, these lanthanoids and actinoids are called as F block elements. Now why are they called as S, D or P or F block? Okay, so these things again I'm telling you, you would be able to understand once you would study the quantum mechanical model. Okay, but no need to go into that depthness. We are just like happy over here. Okay, you would definitely learn those models. You would definitely learn that model, okay, in your higher standards. And then you would definitely be able to understand why they are so called as S block and D block, P block and F block. Clear? So students, coming to the last part of this chapter, which is we have to study some groups, okay, that is group 1, group 2, group 17 and group 18 in slight details. Okay, because since we haven't studied about the periodic table so much, so we will just go through the basic properties of this 4 groups and we will try to understand how the elements in these 4 groups are like behave, or how the elements like behave. Okay, very simple properties. So now here, so first of all for group 1 elements which are there in our periodic table, first we have to remember the names of those group 1 elements. That is simply here lithium, sodium, potassium, rubidium, cesium, francium. I have already given you the mnemonics, LINAC, RBCs, Fra, right? Now whatever properties we are going to see here, these are mostly applicable to this 5 elements. Okay, not they are not more applicable to this francium. Okay, so now what are those properties? Like they are called as alkali metals. Okay, group 1 elements are simply called as alkali metals. Fine, so you can call these elements as group 1 elements or alkali metals. Clear? Now in the name itself, metals, so since their name itself is suggesting metals, they are exactly metals. Okay, fine. State, they all exist in solid states. Valence electrons, they are having 1 electron in their outermost shell. This means the same thing. Fine. And then they are soft. Interesting thing, we can cut them with knife. Wow, it's very easy. Okay, but don't ever think of taking them and cutting them with knife, because like if you take sodium and if you place it on table and if you start cutting it with knife, the sodium would react even with the air present around us. Okay, so much reactive these elements are. Okay, leave about the air. If you would place the sodium on your hand, on your palm, it would even react with the sweat present on your palm. Okay, so it's like very dangerous. These elements are like very dangerous because they are very reactive. Fine. And then lastly, the ionic compounds we have already studied when we were studying structure of atom, right, and chemical bonding. So ionic compounds are formed by these alkali metals with the non-metals. Okay, which non-metals? Like chlorine, bromine. Okay, so for example, sodium bromide, potassium chloride. So sodium is forming an ionic compound with the non-metal bromine. Here potassium is forming ionic compound with a non-metal chlorine. Fine. And lastly, they are metals, so they absolutely would be good conductors of heat and electricity, right? Clear? Now moving ahead to the group 2 elements. So group 2 elements, again we would start with the same thing. We would just remember the names of the element. So I would just give you the mnemonic Be Makka. You just remember 3 elements in this way: Be Makka, and then Sar Ba Ra. Fine, Be Makka, Sar Ba Ra. That's it. So Be Makka, Sar Ba Ra. What are the names? Okay, here initially the names are lithium, sodium, potassium, rubidium, cesium, francium, right? The group 1 elements names. Here beryllium, magnesium, calcium, strontium, barium, radium. Okay, so you need to just remember these names. you would get some time, you would require some time to get thorough with it, but practice would make you thorough. Fine. So names are done. Now mostly the properties would be applicable to this 5 elements. Okay, 1 2 3 4 5. Okay, not more to the radium, the properties which you are going to see right now. So what are the properties? They are called as, okay, means first of all, not starting with the properties, first of all, group 2 elements are called as alkaline earth metals. All these group 2 elements are called as alkaline earth metals. Clear? Now since in their name metals, so now it would be clear to you they are metals. Fine. Their state is solid. Okay, they exist, all these elements, okay, mostly. Now these are the properties, so we are talking about these 5 elements. So these exist in solid state. Their valence electrons are 2, which means that their outermost shell is having 2 electrons. Okay, and their properties are similar to the alkali metals, like they are also quite reactive and all those things, but they are like less reactive than the alkali metals. Fine. Clear? Okay, moving ahead to the next group, group 17. Let's remember the name of the elements of the group 17: fluorine, chlorine, bromine, iodine. Okay, fluorine, chlorine, bromine, iodine, and then astatine and tennessine. Okay, so whatever properties we are going to see, mostly they are applicable to this 4 elements: fluorine, chlorine, bromine, iodine. Okay, now how to remember them? You just remember in a rhythm: fluorine, chlorine, bromine, iodine, astatine. Okay, and the last one is tennessine. Okay, so maybe you could correlate this word because it's like quite fancy one. Okay, tennessine and all those things. So fluorine, chlorine, bromine, iodine, astatine, and lastly tennessine. Okay, fine. The properties, group 17 elements are called as halogens. Now why are they called as halogens? Because in halogen, the hal means salt and gen means producer. Okay, so they are called as salt producers. Okay, now why they are called as salt producers? Because they react with the elements like sodium, okay, and they produce salts. For example, sodium chloride. So this chlorine, which is a group 17 element, they react with the element like sodium and they produce salts, right? So that's why they are called as salt producers. Clear? Example is sodium chloride, we all know, common salt. Clear? Very, very interesting. Now, they are non-metals, very, very clear. Now, talking about their state, very much interesting thing is fluorine and chlorine exist in gaseous state, okay, but bromine exists in liquid state. Superb. And if you would take a look, iodine exists in solid state. Okay, so the state is not same for all the elements. Okay, for fluorine and chlorine it's gas, but for bromine it's liquid, and for iodine it's solid. Clear? They are also quite reactive. Okay, and yes, they exist as a diatomic molecules. Diatomic molecules means their atoms won't exist individually. Okay, their atoms don't have individual existence. Okay, their atoms always combine to form molecule made up of 2 atoms. Okay, so molecule made up of 2 atoms. That's why diatomic. 2 means diatomic. So molecule made up of 2 atoms. Fine, diatomic molecules. Now valence electrons, their outermost shells are having 7 electrons. Clear? And yes, they are like quite reactive. They form ionic compounds with metals. Okay, like for example NaCl or NaBr and KCl, and they also form covalent compounds with non-metals as well. Okay, so yes, ionic compounds with metals, covalent compounds with other non-metals. Fine. Okay, see here. So for example HCl, carbon tetrachloride. Okay, clear? Covalent compounds with non-metals, HCl, carbon tetrachloride and all those things. Fine. And yes, lastly, they are bad conductors of both heat and electricity. Bad conductors of heat and electricity. Clear? Okay. Moving ahead to the last group which we have to study with special reference is group 18. Okay. Oh, sorry, I have just written here 17. It's group 18. This group is called as, or the elements present in this group is called as noble gases or inert gases. Okay. And this group is also called as zero group as well. Okay, fine. This group is called as zero group, and the elements present here in this group are called as noble gases or inert gases. Now from the name you can understand their state is gases. They are all gases. Why noble or inert? Because they are having their outermost shell, okay, outermost shell, okay, the atoms of these all elements are having their outermost shell completely filled. Okay, since the outermost shells are completely filled, okay, or we can say that their outermost shell has completed their octet, so they don't feel any need of gaining the electron or losing the electron, and that's the reason they don't indulge in electron gain or electron loss. So that means that they don't indulge in interacting with the other atoms, not even the atoms of their own element. Okay, so since they don't want any electron, okay, they don't neither they want to gain electron nor they want to lose the electron. That's why, okay, they don't even interact with the atoms of their own element. And why they don't want electron, why they don't want to gain electron or lose electron? Because their outermost shell is like having a complete octet. Fine, clear? Now for that reason they are called as inert, okay, which means that they don't react, okay, or noble gases. Fine, they are monoatomic. So I have told you they don't even interact with the atoms of their same element. Okay, so helium atom won't even interact with the atom with the another helium atom. Okay, so it would just remain as a single atom. Okay, so that's why we say them as monoatomic, one atomic. Okay, so monoatomic gases we say them as. Okay, clear? Since they exist in gaseous state, that's why gases, and monoatomic since one atom. Okay, fine. They are non-metals, absolutely, and they have valence electrons 8, but the exception here is helium. Okay, so I have told you, since they don't react because their outermost shell has completed the octet, there also the exception is helium. Helium doesn't complete octet, it completes its duplet. Okay, but by completing its duplet, helium is very happy. Fine. So what do I mean by happy? It means that it doesn't want an electron. Okay, or means it doesn't indulge in losing electron or gaining electron. So it means that it doesn't react with other elements. Okay, so valence electrons, they are having 8. Valence electrons means 8 electrons in their outermost shell. Exception is helium, it is having 2 electrons. Okay, in their valence shell. Clear? So yes, we have like completed studying the concepts of the remaining concepts of this chapter, the periodic table. Okay, so like you would also be feeling like cheered like this guy. Okay, yes, we have completed. Correct? Fine. Now stop your enjoyment and just try to pay attention, because we are now going to see some questions, so that it would help you like how much you have recollected or how much you remember and how much you have understood. Okay, what we have studied so far in these 2 videos. So first is this like very simple question, match the following. Okay, now the names of the scientists are here in front of you: Demerits, Mendeleev, Newlands, on Henry Moseley. Now what I'm going to do is I'm going to just take a side here. You just have a screenshot and then you try on your own to just match the column. Fine. Okay, because I'm pretty sure that if you have paid attention, if you have understood the things, you would definitely match the correct column, match the correct answers. Okay, fine. So I hope it's done. Okay, fine, let's start. So what Demerits did, out of all these 4 options, okay, he just simply told that the atomic mass of the middle element is the mean of the atomic masses of the other 2 elements in the triad, right? Just like lithium, sodium, potassium, atomic mass of the sodium would be the mean of the atomic masses of the lithium and the potassium. We have already seen that. Now if you want more explanation about it, you can go back to the first video, okay, and get the detailed explanation. Fine. Now next is Mendeleev. So Mendeleev predicted, yes, the existence and the properties of the elements which were yet to be discovered. So that was a great huge breakthrough and great success of Mendeleev's periodic table, or Mendeleev's work, or Mendeleev's contribution towards the development of the periodic table. Fine. And then comes Newland. So Newland told us that, okay, what he observed, that every 8th element has properties similar to the first element when they are arranged in the increasing order of their atomic masses. Correct? So this was the Newland's law. And finally Moseley. Moseley is the one who told that atomic number, very important, atomic number is more fundamental property than the atomic mass of the element. Okay, fine. Okay, moving on to the next question. So whenever you see a question, you pause there, you try to solve on your own, and then you again resume back for the correct answer. Very simple. Don't sit like a couch potato and watch the video as like you're watching a movie. Okay, this won't help you because your brain won't work. I always tell in each and every, almost I think in each and every lecture. So maybe it would have impacted you. Fine. Let's see the next question. Come back to the question and out of the philosophy. The number of elements in the 7th period of the periodic table is. So if you would have remembered it, you would have been knowing it. So the right answer here is not 18, not 36, neither 8. Okay, it's 32. Fine. So number of elements in the 7th period of the periodic table is 32. Okay, fine. Moving ahead, which of the following statement is correct with respect to the elements? sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine. So we have to see which of the following statement is correct. Okay, just keep your brain calm and try and read the question first with calmness. Okay, otherwise you would end up getting the wrong answers. So which of the following statement is correct with respect to the elements this? Fine. So let's see the statement and let's decide which of the following is correct. Each element belongs to the same group. Absolutely not, because sodium and magnesium and aluminum, they don't belong to the same group. Fine. Sodium's group is like lithium, sodium, potassium, rubidium, cesium, francium. Okay, so since I remember the names of the sodium's group of elements, because sodium belongs to the group 1. Okay, so this is how you would use your knowledge. You would use the entire thing which you have learned so far and then try to answer the questions, right? This is how we apply the knowledge. This is how we solve the questions. Fine. So each element belongs to the same group. Absolutely not, because sodium's group is like way different and neither of the element is present here which is belonging to the sodium's group. These are not the elements which are present in the same group. Okay, if suppose here the elements would be like lithium, sodium, potassium, rubidium, cesium, francium, then I would say that each element belongs to the same group, right? But it is not. So this is not the correct, and we have to get the correct statement, right? Which of the following statement is correct? So this is not correct. Valency of each element is same. Absolutely wrong. Sodium's valency is like 1 and magnesium's valency is 2. If you would know the valency concept and if you would have remembered the valencies, okay, it would be very easy for you. Sodium's valency is 1, magnesium valency is 2. So no, valency of each element is not same. Okay, so valency of each element is same. It's not same, right? So it is also incorrect statement. Okay, we need to find a correct one. Then each element belongs to the same period. Oh, can you just go through the periodic table second period? Okay, the second period starts from sodium and it ends with argon. Okay, so here from sodium, if I would start writing the names of the elements in the increasing order of their atomic number, okay, sodium is 11. Okay, so magnesium, aluminium, like, right? So sodium, magnesium, aluminium, silicon, phosphorus, right? And then again sulfur, chlorine, and then comes argon. Okay, so I just made the mess here. Okay, phosphorus, sulfur, chlorine, and then argon. Fine. So 11, 12, 13, 14, 15, 16, 17, 18. Clear? So see, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine. Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine. They are all belonging to the same period, the period number 2. If you don't believe me, you can just have a look over the periodic table. You would get it. Okay. So each element belongs to the same period. Yes, absolutely. Okay. So this is the correct statement. We got a correct statement. They are all metals. Absolutely wrong, because sodium, magnesium, aluminum, these are metals. But yes, our chlorine, we have just now seen halogens are non-metals. Okay. So they are not all metals. Fine. So this is also not correct. They are all metals. This is also not correct. So the correct statement is this one, C. Okay, fine. Okay, let's move ahead. I will now show all the options and then you try it on your own by resuming the video. Okay, by pausing the video, sorry. Fine. I hope you would have tried on your own. Let's see the answer then. Elements with 2 electrons in the outermost shell. With the 2 electrons in the outermost shell. Just now we have seen the group 2 elements or the alkaline earth metals are having 2 valence electrons, which means 2 electrons in the outermost shell. So the answer is very much pretty clear to you, alkaline earth metals. Okay, so alkali metals no, halogens no, noble gases no, alkaline earth metals, right? Alkali metals, now let me tell you, alkali metals are having 1 electrons in their outermost shell because valence electrons are 1 in case of alkali metals. Halogens are having 7 electrons in their outermost shell, okay, because valence electrons are 7. Noble gases are having 8. Alkaline earth metals are having 2. So our right answer is 2. Clear? So friends, with this we have reached the end of this video and I hope you would have enjoyed learning with me. You would have understood the concepts which we have learned so far, right? But please do let me know this thing in the comment section. I would be waiting for your comments. And yes, as you all know, learno matlab free hai par best hai. Also, along with these videos, after watching these videos, after going through your texts, after solving some questions in your textbooks, if you are like really enthusiastic to solve more questions, and I definitely feel that you should solve more questions, so for that purpose you can visit our website learnohub.com. we have made fantastic daily practice problems, okay, and online tests as well, which you can solve. so that you would get more practice of the questions and your brain would get open to solve more questions, right? Your problem solving mindset would develop. Fine. So that's it, and let's meet in the next video with the next concepts, okay, the new concepts of that new chapter. Till then, keep studying, stay tuned, bye bye, and have a great day.